Welcome everyone to the group chat brought to you by OVERMUGGED. I'm your host Daryl, and today with me I have someone very special. Special because I've known this guy for more than half my life, and that's none other than tutor Gerald.
Hello.
Gerald, why not introduce yourself to the viewers?
Hello. Shout out to my students first. If you're my student listening to this, a big hello to you. Thank you for tuning in. It's my first time doing this, but I would want this to be as casual as possible also. So thank you for listening in. I'll share with you physics tips.
Yes, today's topic is on how do you score an A1 for O-level physics. Good news for the listeners, both me and Gerald will be teaching O-level physics for a really long time. But I don't want to take away too much of the limelight from my brother over here. So Gerald, why not you hit right in? If a student wants to score A1 for O-level physics, what must they do?
A1 for O-level physics. It's actually simpler than you think. I give a short intro of it first. The very basic line to it, right, is be a mugger. Since we are an overmarked podcast, right, be a mugger. Okay, nerds are really like underrated. Like people say, wow, this nerd like very lame. Actually, at the end of the O-levels, right, if you're a nerd, right, then you're like, this is my result slip. Versus those like, wow, very cool and like, this is my result slip. Yeah. Okay, so bring out that inner nerd in yourself. Yeah. And for physics specific stuff, right, one true thing is really you need to understand physics, not memorize physics. I have students coming in telling me that one day before I go and study all the definitions and all, then I went into the exam thinking I can do well. Obviously, they came out and the reality is I did not understand half the questions. So if you are guilty of doing that for physics, you really cannot if you are serious about getting the A1.
Yeah, I think that's super true because I think a lot of students, we have the preconceived notion that, physics is about formulas. So what we do is we memorize formulas, hoping that when we go into the exam, we can do well. But the truth is, if you look at how papers are evolving and how Cambridge is setting questions, they are no longer testing for, say, a lot of definitions or regurgitation. A lot of times it's about applying that concept and solving more unique scenarios. And if you fall into the trap of always memorizing only, then you tend to miss out on a lot of the ability to solve the harder questions. If I can go into detail here, right, just one example. One of the most famous formulas in physics is F equals to ma. But if you are my student or if you're here at OVERMUGGED, you realize it's not F equals to ma. Because F equals to ma is a formula.
My students too.
It is what? It is RF equals to ma. More importantly, resultant force, right? So you have to account for all forces acting on the body first before you take mass times acceleration. So it's not just about memorizing the formula, but it's about understanding what that F stands for, is resultant force. So that makes a huge difference because it's either you get the question correct or wrong. So going back to the point, don't just memorize. But let's break down the physics paper, right? Because there's a few papers over here. So there's paper 1, which is MCQ, paper 2, that's structured, and paper 3, which is your practical assessment. So Gerald, how much is each paper's weightage? And if we are looking to score an A1, roughly what is the percentage we should be looking at for each paper?
Just get full marks for everything. Confirm A1. Okay, but I really feel that when you go into the paper, right, you should aim for full marks. You cannot be like I go and count, I purposely leave out one question that I will get 70 out of 80. No man. Right? Because at the end of the day, you may get some questions wrong and that's fine. I finished the whole paper. I have tried my best now. Yeah. But going to the breakdown of the paper, you're right, there are 3 papers over here. Paper 1 MCQ is actually 30%. MCQ is really more important than you think. I had a casual chat with my student just last Saturday where I was giving out prelim papers. Here at OVERMUGGED, we're like so big on prelim papers. We're gonna whack, we're gonna do question analysis and all. Then when she received the paper, she flipped through the MCQ, she's like, wow, I realized MCQ physics, right, a lot are actually repeatable, like maybe they change some values and all. The questions are pretty much the same. And this is the reality of it. If you want to score well, 30% is easily attainable. Reality check, 40 out of 40 is of course the aim, but my personal take is 35 out of 40 is really a safe zone for you to go. Yeah. Then we go to paper 2. Paper 2 is 50%. There are 80 marks. Same thing, should I aim for full marks? It's definitely a yes for me, but in reality, not very possible, right? So I would say marks you should aim for when you study or when you try your practice papers is 60. Yeah. Losing that 20 marks could be, say one question, maybe you lose about 2 marks. I think that's very, very fair because the whole paper is like, there are about 10 questions. So there are confirmed weird questions. Right? Every single year got one weird question. Yeah, so if you don't get that one question part, I think it's still fine. Like 60 out of 80 will be very comfortable. Then paper 3, we have 40 marks in total, 20%. Some students are like, I have students from this particular school. If you are listening in, I won't name your school, but you have complained to me that my physics teacher never do any physics practical at all until this year. Sec 3, we never touch it all. Only thing we did, go to the lab, we swing the ball right and left. And you go and time. Right. So this 20% is like more important than you think. So this 20% actually can make a difference in at least one grade jump. Yeah. So out of 40 marks, I would say you can score 30. Definitely things that you can prep for. We are going to prepare you guys during the O-level mock practical that I really wish you guys will join us with. Yeah, so aiming a 30 or 40, you may lose some marks here and there for some maybe careless mistakes or some like very, very strange questions. And that's fine. Yeah, so 30 or 40 will probably then you at that A1.
Yeah, I mean, just to add on, I think everything Gerald said is true, especially for paper one. I think it's so underrated. Now, in terms of timing on when you take your O-level MCQ, it's actually after all of your exams are done. So your science MCQ is always the last paper that you take. And usually by this time, it's about week 3 or nearing week 4 into your O-level. Most people start letting go already. But that's actually one of the worst things that you can do. If you think about it, right, paper one with a weightage of 30% with 40 MCQ questions, it means that on average, one MCQ is worth a 0.75 of your overall grade. This means just simply getting 3 or 4 careless questions wrongly is a 1 grade difference. So MCQ paper, I can't emphasize enough, which is why at Overmark, right, before you go for your MCQ, you'll be taking 400 MCQs. Yes, so you'll be doing all 400 MCQs, we'll be going through all 400 before you sit for your O-level so you don't slack off. So MCQ is one of those hidden components that I say is very important. The other one is really on practical. I think enough has been said on how important it can be in terms of a grade shift. Is the difference between an A1, A2 or A2 and a B3. Now, for practical itself, it's really about ample preparation. I have one baseline, which is that if you go into practical, not knowing what you are supposed to do, you're in trouble. It means that if you're given the electricity setup, you should very clearly already know, what to be looking out for. Do you know to test for your battery, test for your ammeter, voltmeter, to check all the components before you set it up? What are key things to look out for when you're setting up certain experiments? Do you already know your precautions and sources of error? These are all things that you can prepare beforehand, right? And these are all things that you can study in the practical curated notes. So the minimum you can do is at least to get yourself ready for those segments that you know I can prepare for. Of course, the actual experiment that come out might look a little different from what has been tested in the past. But what is left from there is just, following instructions. Things like your graphing technique, learning how to linearize your equation, these are all things you can prepare for beforehand. All right. So when we break down each individual paper, cannot say that one is more important than the other because all of them matter. But if we shift the gear here a little, right, instead of talking about the exam format, Gerald, if we move our attention more to what is Cambridge looking for in a candidate, as a physics student, what are certain skill sets that we need to be able to have in order to do well?
To summarize this point, right, I really feel that you need to be fast yet accurate. I know it sounds very like everybody, like every single subject needs me to do this. But for physics, as said, right, like you need to really understand instead of memorize physics. So the fast part is really not of how fast can I write my answer. I was a pure history student, so I know how fast you need to write your humanities answers. Right, when you miss out the year in which Hitler got assassinated or killed himself, then you're like, I'm not gonna score the marks. But for physics, you need to be fast in terms of your thinking. Are you able to apply the concepts quickly, draw the correct ideas from the correct chapters, throw it in, able to apply the relevant formulas and all into the question? If I were to say Cambridge, what are they looking for, right? They are really looking for someone who can apply concepts to different scenarios. I bring you back in time 1 year to 2024 levels. The very first question on kinematics, right, if you have done your TYS, was the ball bouncing. Right, the ball bouncing was not just a simple ball bouncing as in like you draw the graph, zip, 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 this way. No, if you did that, you're screwed. Right, but if you really understood and dive deep down into the physics question, the physics behind it, you would see that that particular question, right, like there was air resistance. If there was no air resistance, true, you would draw this, but there was air resistance, meaning do you need to consider curve? Do you need to consider straight line? As well, when the ball bounces and hits the floor, what do you need to consider? There was a time frame in which the ball hits the floor in that particular question. Right, so if you don't know what I'm talking about, right, you can port over to your 2024 TYS. For my own students, we are definitely going to break down that question together. Then one last point on what Cambridge really looks for is really a seasoned student. Again, this is pretty generic, but I still want to dive deep into this to say that Cambridge really wants you to be so numb from the practices you have done, right, that when you go into a paper, you really are truly ready. Right, to build on Daryl's point, for practical even, if I shift away from paper 1 and 2, for practical, do you do enough preparation for planning? Do you know the skeleton for planning? At Overmark, we teach you the skeleton of the planning. you don't even care about what question it is. You go in, you see the blending question, you're like, oh, it's these points. I already know the rough framework that I'm gonna have. That will pretty much guarantee your planning is, if 5 marks, I got at least 3 marks already. Yeah, my students listening to this, you will definitely know what I'm talking about.
So, I mean, adding on to that point, right, it's the same as graphing in practical. Do you know what is SLAP, right? Your scale, your line of best fit, your axis, as well as your points. So you already know where you'll be given marks, and therefore it's so much easier to score well. So I would say, if we're talking about, what is Cambridge looking for in a student, right? It's really no longer about memorizing definitions and formulas. It's about your ability to solve questions. And they're coming out with more and more novel and unique situations that you need to apply your physics concepts to. So don't be fixated on I can memorize science, because if you do that, I guarantee you will not get your A1, right? You actually need to understand the concepts. While it will take longer and it comes with some version of a practice to really understand the concept, in the long run, it makes a lot of difference. Now, let's not go generic, let's go specific now. So there are multiple topics in O-level physics that generally students will find more difficult or tricky. So we're going to go down the list of some of the more common chapters that students struggle with, and to pinpoint exactly what are certain things to look out for. So maybe we can start with one of the scariest one, which is dynamics, right? So Gerald, for dynamics, what is it that students need to look out for?
This one, right? Like a bit exaggerated, right? But what I like to say, right, is can you explain Newton's laws and terminal velocity with your eyes closed? My own students, I think you will know exactly how our class runs, right? When I give you a terminal velocity question, are you just copying down every single answer line that you see? Or are you doing what we do in class best? Like we write down a point, we arrow, we keep flowing the answer, as in how the answer should flow in your thoughts. Right. So to be specific, terminal velocity, are you able to tell how air resistance acts against weight? Are you able to tell how when you run to the bus stop versus you walk to the bus stop, like which one more air hit your face, which one got more air resistance? These are things that I've said a lot of times, that every single marking scheme that I see, right, they are allocating about 1 mark to that. So if you fail to bring in that particular points, then you are bound to not get full marks for that question. Yeah. So can you explain terminal velocity well in that aspect? Yeah. So the next thing is something I like to say is, I drag one of you, we jump down from a super high building together. What is our initial acceleration? Why is it the same even though I am much heavier than you? Right? Then these are things that we have discussed before in class, and like what Daryl was saying, Cambridge is really thinking of novel situations, new situations. How are you going to apply this concept of terminal velocity? Right? Then with parachute opening, we just talk about now, right? Just the person jumping down or reaching terminal velocity, sure. What if you, after O-levels, you want to go and do skydiving with the permission of your parents, of course, right? When you jump down and am I supposed to go and feel the terminal velocity? Or am I super scared that I need to open the parachute very fast? Then will there be a second terminal velocity when I open the parachute? How is the graph going to look like? With air resistance, is it going to be a curve, or is it still a straight line? Right? If these things are quite blurry to you, I forgot all of this because I learned in Sec 3. Yeah, these are things that you need to trigger a memory about. And with your eyes closed, right, are you still be able to explain this?
Yeah, because if I were to dig a little deeper, if you all really pay attention to the learning outcome according to your syllabus, you are not required to memorize Newton's 3 law. They won't ask you to define Newton's first, second, third law. All they will ask you to do is to apply the laws to different situations and to be able to explain, right? So Newton's first law is inertial, right? Can you apply inertial to an object at rest versus a moving object? Newton's second law is about resultant force. For example, an object moving at constant speed has 0 resultant force. And Newton's third law, one of the most famous one, is the action-reaction pair. Do you know what are the 4 conditions for Newton's third law for an action-reaction pair? All of this needs to be internalized and applied to multiple situations so that you fully digest it, so that in the future you can apply it to more novel situations. If we move to the next theme, right, thermal properties is one big one. So Gerald, what do we need to look out for thermal properties?
I really feel the biggest confusion here, right, is if you are listening to this and you're like, oh, this is really the topic that I really hate, right? If you didn't understand what was required of you in the first place, right? Because if they just look like random numbers and random words to you, maybe you'll be like, I don't know when I need the MC theta theta, I don't know when I need the MLF. If you are guilty of this thought right now, right, the biggest thing you need to take away is really when to use capacity, when to use latent. right? Latent, then one more layer of fear that you have will be, wow, fusion and vaporization, like so strange. All these words sound like so new to me. I don't know what to do with them. But the moment you are able to understand capacity is temperature change. Latent is state change. You will be able to map that onto the heating curve or the cooling curve. That's where you truly unlock what you need to solve the question. Right. For those weaker students, I told you, you can start off by drawing a number line, sort of like a temperature line for you to see, oh, if temperature shifts, if temperature changes, we use capacity, right? But if there's only a state change, then we will use latent. Then when we draw on the number line, we are very clear. We label, oh, when do I need capacity? When do I use latent, right? So I think the biggest one is really when can you use capacity and when should you use latent. Once you unlock that, you're fine. Evaporation. I like to say, oh, we try to reach for the A1, but your bad friends are pulling you down. Okay, so if you have bad friends in school, right, then you might be like, wow, my friend always asks me to go and not study, ask me to go and chill after school. Those are your bad friends that are like pulling you down, but you are the energetic particle trying to reach for the A1. Yeah. Okay, so these are like ways that you can imagine physics a little. Because honestly, when I see evaporation, right, in real life, like put my cup of drink over there, then I watch it for a few hours. Do I see anything? I don't, ma. Right? If you can picture physics a bit more like, can it come to life? Then the understanding will be much nicer.
Yeah, definitely. I think it really boils down to understanding. Because when we use like heat capacity, it's actually about the IKE. Because it's about change in temperature. And if you look at latent heat of vaporization, latent heat of fusion, it's about change in state. It's about an increase in the separation between the molecules, which directly relates to your internal potential energy. So it's about having clarity over these concepts that will help you out in the long run. The next big chapter that I always think students struggle with is waves, right? So particularly in terms of how the particles behave. So Gerald, what is, I think, one misconception or one thing that you think students till today do not have clarity about?
You listening right now, right? If I ask you this question and you cannot answer, then you need to rethink a little on waves, right? Is there a difference between wave speed and particle speed? It's a dramatic pause for you to think, not the answer. Yes, there is a difference, right? So wave speed and particle speed are actually two different things. Particle, you are actually looking at one thing just vibrating, but the wave is how the energy is being passed on, right? The famous V equals to F lambda. Is that really for wave speed or is that for particle speed? That's something that you should know and you must know to go into it, right? For particle vibrating, my students will definitely know this idea of shutter run, right? So if you imagine a particle doing a shutter run, then you will be able to imagine how it's vibrating, right? From the start position, how it's going to go there and run for the block, grab the block and run back, right? So particles always will go back eventually to an equilibrium position or to their starting position after one complete cycle. Right.
So just to be clear, in case it's not clear, wave speed is your V equals to F lambda. The one that I think most of you know. Particle speed is about during its oscillation, when does it have higher speed, when does it have no speed. Alright? And when you visualize it, I think it's a lot easier. So if you keep going back to how me and Gerald, we think about physics, how we teach physics, it's really about putting it in a scenario that we can understand. Right? Because right now, you might not be able to visualize how a particle vibrates, right? Whether it's up, down, or left, right? But when you put it in context of somebody doing a shutter run, you can easily imagine at the point whereby they turn around and they go the other way, which is at the crest and the trough, that is when they have zero speed. Because it's about coming to rest and changing direction. And in the midst of the sprint, as it's going past the equilibrium, that's when the particle speed is the fastest. So really about applying all of this, I would say imagery in your head really goes a long way, because that way you don't have to memorize really, right? Because you really understand the situation. All right, another monster of a chapter is electricity, right, Gerald? So how can we break down this chapter? What is, one concept that students always struggle with?
Like series and parallel in series. Does that sound scary? It shouldn't, right? If you are able to simplify a complicated circuit into one that's easily digestible, that's actually really, really easy for you to do. Right. So for example, if I have a complicated looking circuit that has like a lot of parallel parts to the entire circuit, am I able to circle each of it and tell myself, oh, if I find the effective resistance of this, I can actually simplify it to look like a single resistor. With that, then all the parallel all connected together, if you make them one all joined together in series, then all you need to do is to add. then you will get the total effective resistance, right? So, and another thing that people hate is really the potential divider, right? Potential divider, if you think about it logically, if you truly understand the idea, personally, I even go down or rather go back to primary school to bring in the idea of a model drawing. If you draw a model for potential divider, you'll be able to see, actually it's just the battery, right? Trying to decide how much potential should I give to each of the resistor. If you have more resistance, I give you more potential. You have less resistance, I give you less potential. Right. So if you draw a model, you understand what I mean by the number of units that the battery decide to give is based on your resistance. Yeah.
So I think adding on to potential divider, I think all of my students would know this. When I first started with potential divider as a concept, I insisted on not looking at the formula. Why? Because the formula is I always feel, right, it's never about the formula. It's about understanding the concept. And then when you look at the formula, it will make sense. Because I think what Gerald is trying to also like emphasize the same point, right, which is that how a potential divider works, if you think about it, is how you divide up the potential difference. So if the EMF of the battery is 12 volt, how do you split this 12 volt between the different resistors? How you split it is according to the resistance ratio. The resistance ratio will help you split the voltage accordingly. And when then you go back to the formula, you will see the way it's structured. It's in the form of calculating ratios. Then suddenly, right, it's not about memorizing the formula, but you understanding the concept, and therefore the formula makes sense. So that should be the correct way that you go and learn physics rather than starting with the formula. Because at the end of the day, the ability to apply it to different situations to solve questions is still the priority. But of course, if we move on to sort of like the next monster of a chapter beyond electricity, is definitely the chapter on magnetism, all the way to electromagnetism to EMI. So Gerald, what are some of the things that students commonly mix up over here?
Some people like to do this, right? You don't know which one is the left hand, which one is the right hand, right? Okay, so number one, make sure you know which one is left, which one is right. I have friends, right, learn driving and instructor say turn left, then my friend need to do this. Oh, left is this way, okay, I need to turn the steering wheel this way. Okay, that's number one you need to focus on. Okay, then of course the chapter started off actually with your right hand grip rule. Right. So right hand grip rule actually, like you need to know which scenario to use which. Because right hand grip rule actually got two different users. Like, are you sure on which one is the solenoid one? When you see coil, you use right hand grip rule for what? When it's a straight conductor, you also use right hand grip rule, but then for what? Right? So these are things that you need to be sure of. After which, then we saw Fleming's left hand rule. Right? Fleming's left hand rule is honestly, right, just a shortcut. Have you realized that? Fleming's left hand rule is a shortcut. It's after you combine all the right hand grip rule together, how they interact and all. Fleming's left hand rule is just like a shortcut for you to quickly find the force. Right? You have the current, you have the external magnetic field, then there's a force experienced by the conductor. Right? Then the famous one that I picked up from Daryl as well is the father, mother, child, right? That one is inside our creator notes also. Right? Then you must know like how to make this a bit more fun. My mother always point finger at me and all. Yeah, so with that, then your magnetic field, current, force, you will never mix up again. No? Right? Then the very last thing that I can say before Daryl starts, right, is Fleming's right hand rule. Right. Between these two, like I may be joking about this, right? Like, of course, I know a lot of you know your left hand, right? But the true question in physics is like, when do I use Fleming's left hand? When do I use Fleming's right hand? It's honestly not about, in this question, I saw that I have a current, I saw that I have a magnetic field, hence I use left hand. It's not true, right? You need to see in the question actually what is the one that is actually present. And then you decide, since these two are present, I use left hand. Since the other two are present, I use right hand. Are you able to dig deep into a question like this? Because the prelim papers that we are going to do, honestly, the MCQ actually got one bring up this point best really. So you can look forward to that for our own students, because we have 5 prelim papers coming up for you, right? The 2024 prelim papers.
Yeah. I mean, to add on to that point directly, when to use left, when to use right? I always got my students to remember this. When I play Mobile Legends, right, I always get wrecked. So MLGR. So ML stands for when you're looking at DC motor, you use your Fleming's left hand rule. So ML. GR stands for if you see a generator producing electricity, then you use your Fleming's right hand rule. So the way I always approach physics is how can we simplify it for ourselves? Right? How do we make it easier to recall or to bring out concepts so that we don't have to memorize them? So the ability to do question analysis, to identify which is the correct rule to apply, and therefore to solve questions is always the priority. Knowing your Fleming's left hand rule alone doesn't help, but can you apply it to a DC motor question, to to understand, oh, is it going to rotate clockwise or anti-clockwise, right? Why is a split ring commutator there? And when is it a slip ring? Those are all key differences. So I would say the chapter here is a lot more difficult, especially for those that are looking at a chapter in electromagnetic induction. Do you know when to bring out Faraday's law? When to bring out Lenz's law to explain different situations, right? Faraday's law is meant to help you explain questions where they're asking you, oh, why is there a deflection in the galvanometer? Why do we produce electricity? It's about the change in magnetic flux. But then for Lenz's law, it's more about the direction of the current. Will I form a north and south pole? How does that affect my right-hand grip rule to cause current to flow in a particular direction? So it's really about the precision and how specific you know each concept that guarantees your success. This is traditionally always one of the weakest topics for students. So generally, I recommend doing more revision on this as it's one of the more shaky chapters always. And to wrap up, right, for radioactivity, right, this is a new chapter. The existence of questions are not as much, but for our own students, we have collated about 20 plus clues worth of prelim, and we have set out the better radioactivity question. And I mean, to just summarize on this point real quick, it's really about, do you know what is your half-life? And do you know what is background radiation? Alpha, beta, gamma rays, right? Those are all specifics. Actually, it's not a very difficult chapter, but it's one chapter whereby you do need to build some level of understanding. Jared, anything else that you think we need to look out for radioactivity particularly?
I'm quite big on the penetrating power. Yeah, the alpha, beta, gamma I mentioned, right? Yes, you need to understand on how the radiation are being released, but the penetrating power is something that I've observed quite a lot of schools are actually or tested on last year. On which one can penetrate the most, which one can penetrate the least. In fact, the questions that we received out, there are some questions like smoke detector. Smoke detector, why are alpha particles being used? What's the logic of doing this? What's the advantage of doing this? Right? So they can be easily absorbed, won't like penetrate human skin, they can't even reach us in the first place. Right? Because I have a smoke detector at home. If the alpha particle is gonna come into my skin, right, I'm dead. Right? So we need to know like, these are like practical uses of smoke detector of alpha particles. So I'm big on the penetrating power.
All right, we're gonna go for a quick advertisement break and we'll be right back.
I hope you have been enjoying the contents of the podcast so far. If you want to find out more about the latest study tips and exam strategies, do check out my free ebook that you can download on our website. Additionally, if you are curious about how OVERMUGGED classes are like, feel free to join us for a free trial lesson anytime. Back to the podcast.
All right, welcome everybody back.
Hello.
Now, we have really talked very specific topic by topic, but at this point, right, I want to focus more on revision strategy, right? Perhaps right now we are perhaps few months to O levels. So as a student right now, what should my focus be? Do I go topical? Do I do TYS? Gerald, what's your advice for students tuning into this podcast?
I received so many of these questions also. Like my student currently, if you're listening to this and you have asked me this question before, I think you would know, what should I do now? I think that's the $1 million question, right? I've studied so hard. I have been so consistent. Right now, I have identified a few chapters that I'm weak in. So I would say topical TYS, simply put, is a really, really good starting point. Right? At the end, like when you're really close to O levels, should you still be chonging your topical TYS? I would say no. Right? But right now is for you to identify, I'm really bad at drawing Lenz diagram, for example. What if I drill down into topical TYS, / if I ask my tutor for like, can you give me some questions for me to try? And I'll be like, sure, I'll send you some questions for you to try. Then you drill down into those chapters for you to try. Like, am I able to get this right? Especially topical TYS, right? It's like, you are actually going to see these kind of questions. You are really going to experience this. Hence, I need to make sure I truly understand 100% of everything that I try. Right. So it's really a good starting point because you can even practice down to drawing, answering skill, calculations. Right. Then you don't have to sift through a stack of grading paper that your school probably gave to you already. Like some I hear 10 plus. Like, okay, now give. Then you have to go and sift. Like, okay, I go and try. I need to check the answers. Yeah. So topical TYS to me is a good point to start.
Yeah. I will also recommend starting with your weaker topics first. So there are some topics you know you're just okay in. Right? Don't go and spend more time confirming you already know what you know. Instead, spend the most times on questions that you are unable to solve right now, because the ability to solve those questions is where the improvement comes in. Right? So also know how to prioritize which chapters to start with. Now, on the point of prelim papers, right? Should students be grinding prelim papers? What's your opinion on it, Gerald?
I received a question on grinding prelim papers versus grinding TYS. Should they work hand in hand, or should I start with prelim papers now, or should I start with TYS? I would say, honestly, there's no right answer to this. Yeah, not a very popular opinion perhaps, but I would say TYS should be actually doing it as you prepare for prelims also. Right, some people believe prelim like so much harder than TYS. I do TYS, got use man. Right. For some of my students tend to score a bit better, right? A common trend that I saw, right, is they actually do their TYS before their prelims. Why is that the case, right? Some schools actually recycle some TYS questions in prelims. It's a reality. And TYS questions, right, when you try, then you are like, oh, so these are the certain trends that Cambridge likes to test, which your school will actually try to replicate as well. So I would say, yes, you should definitely do TYS. But that being said, right, should I just focus on TYS? It's a real no, right? Because you are definitely right to say that, oh, maybe TYS standard is like lower compared to my school prelim papers. And rightfully so. I guess all schools are trying to like prep students as much as they can for the final one. But at this stage, you really cannot ignore prelim papers. Why is that the case? Because schools are like, they attend this kind of briefings with Cambridge, right? To like, certain things that students need to look out for. So perhaps those like position holders, they know certain trends that Cambridge feeds to them, then they're like, oh, so we should prepare students more in this aspect. So prelim papers is really one big thing that you should look into. And it's really not at this point that you should say, oh, I whack prelim papers, I just like casually do at my own pace and all. Right? Should it be the first time that you go into an exam like, oh, I don't even know how much time I'm allocated for paper 2. I just like, okay, I YOLO, I just go to the exam and I'm given 1 hour and 45 minutes. Your time starts now, I start doing. No, the strategy going in, right, when you do the papers right now, it's not just, oh, I want to practice questions. It's I want to practice doing questions when I'm stressed. Right? It makes a whole lot of difference. Like you casually ask me to do paper after paper, I can. Right? But if I put you under time stress, are you able to like manage that and able to like, oh, I allocate this amount of time to each question?
So that boils down to your time management strategy in exams. So going back to practice, yes, you should do practice, but highly encouraged to do it in a time setting. I will also go back to this point of like there's a concentration stamina, which is how long can you sit down and fully concentrate without like losing focus, right? And that comes with the necessary preparation work for your prelim, because in prelim, you'll be sitting for a full paper, right? Are you able to concentrate from start to finish, or will you give up halfway? Now, it's very natural at this point in time, with most of your content sort of settled, you'll be doing a lot of practices. But one point that we always emphasize on is not only doing more practices, but making sure that you get your corrections done. So perhaps we can dig a little deeper, Gerald. When a student is doing corrections, what should they look out for?
Corrections, as I always advise, right? Copying down answer word by word. I've spoken about this just like 10 minutes ago or so. It makes no sense. Like when you look on the screen, you're like, oh, I'm so worried about capturing every single word that the answer key has. Is that really truly understanding? I would say no. Right? If you are one that like, oh, I copy down first, play safe, I go back, I will look through it again. Do you truly do it? Right? So at that point, why not spend the time to understand the thought process? Why not spend the time to understand the question breakdown? That will help you so much more. Because honestly, might you see the exact same question? I wouldn't say it's impossible. There are certain cases that have occurred before, but will you truly have a 100% chance of seeing that question? It's a no one. Actually, it's like a 10% or less chance of doing so. So why not spend the time understanding, oh, certain keywords that I see, like I drop the ball from rest. Once you see the from rest, initial velocity is 0. Right? Then you can apply certain formulas like A equals to V minus U over T, etc. Right? So these are things that you should spend. Like I highlight certain things in the question. Then when I need explanation questions, which I believe a lot of students are struggling with, like how do I start my answer even? Like what concepts do I draw? Right? So these are things that you should look out for when you try a question, instead of like, oh, I do corrections means I must write down every single word. Then you need to be consistent about it. Answering techniques are answering techniques if you are consistent. If you choose to be like, oh, sometimes I write this way, sometimes I write the other way, then your answering technique, is it truly a technique that you will apply in exam? So when you do corrections, you should be like, oh, I see this kind of question. For example, like what Daryl was saying, why the galvanometer deflects? We know that it's a Faraday's law question. How do I phrase Faraday's law? Do I need to talk about change in magnetic flux? Or should I talk about Lenz's law? This kind of things. Right? So when you do corrections, you'll be like, oh, since the question asked this, I need to apply this particular concept.
Yeah, I think that's a very good point. I think doing corrections is actually how you learn. But let's perhaps sum up, right? If Gerald, there's one last part to this whole podcast, which is, careless mistakes is a big thing. I think especially in physics, that happens to pop up quite a lot. So what do you have to like, call out to students that always claim that they are having a lot of careless mistakes?
Is your careless mistake truly careless? That's the first question I always ask you. When I look at your school exam papers, right? Then my students will always show me like, this one I careless. Then I look at the paper. Is it truly you are careless? Or is it when you read the question, you were not like precise enough in highlighting a certain point to make you avoid that careless mistake? Right. So actually it's avoidable. Some of these careless mistakes are truly avoidable. Careless mistake, in my opinion, are like my calculator show 3.02, but I go and write 3.08. These are careless mistakes. If your careless mistake is like, oh, I used the wrong distance when I calculated moments, is that truly careless, or is it like you didn't draw the line of action in exam to avoid that careless mistake? Right. So for each topic, you need to know that there are actually certain tricks for you to avoid this careless mistake that you guys claim, because that will actually help you go above the rest. And like, oh, while other people are making these careless mistakes, I'm actually not, because I do certain tricks and tips that I know in exam to help me avoid them altogether.
For me, about careless, right, is about prevention. How do you prevent yourself from making careless mistakes? So I always tell my students, right, you already know where you're going to make a careless mistake. I already tell them already. So for example, when it comes to chapter and light, right, all my students will know this. I will nag them till the end of earth, right, to freaking draw a normal, right? To remind yourself to always use the angle between the light ray and the normal. Because the questions will always give you the other angle, right? And that is when you make careless mistakes. But it's not truly careless because you already know how to avoid them. So when it comes down to careless, you always boil back down to how can I prevent making the same mistake again? Do you have a foolproof method in place? So for example, when you're doing other question types, even let's say in waves, for example, right? Do you know what to look out for when you're looking at a graph, right? You need to focus on what the x-axis is to know whether one wave is wavelength or is one wave a period. So you already know the focus is focusing on the x-axis. And if it's time, is it in seconds or milliseconds? Because that will affect your calculation for frequency, right? So you must already know these mistakes. And how can you build a database? What I always ask my students to do, right, is that if you have the time, every time you make a careless mistake, you note that down. You can take a photo of the exact question, right? Save it in a folder or something. So you have this like entire folder, which I call the mistake bin. So you can go back to this mistake bin to look through, okay, among all the physics chapters, right, these are 50 mistakes that I made in the past. The day before your exam, just look through. Don't even have to solve the question again, but go and pre-identify what was the mistake that was made. And promise yourself that you are aware clearly and you will not make the mistake again. That is what we truly consider learning. So to end off this podcast, right, Gerald, if you have just one last shout out, right, to Sec 4s listening to this podcast, taking their O-level soon, what would you want to tell them?
I'm a nerd, right? It's back in Sec 4, I studied so hard, right? And I like to say this, if I were to really turn back clock again, X number of years, right? Back to when I was 16 years old, am I gonna study less hard and like play a bit more with my friends, go out and chill a bit more with them? The answer is no. If I were to turn back the clock, right, I would study as hard as I did and live with no regrets. And really, I want to shout out to all my students, right? Hard work will be rewarded. You all learn in SS also, right? Reward for work for reward, right? So if I have a last shout out, please don't leave any regrets that I should have studied harder. Go for it.
Yeah, I can attest to that because usually after our floorball trainings, after our CCA, Gerald never ever joins us for dinner. Then we'll go to the land shop, we'll play all, but he never joined us. But the reality was that he scored better than all of us. So take it for its worth. We are real life examples and proof that hard work does pay off. All right, so we have come to the end of the podcast. If you enjoyed this podcast, thanks for tuning in all the way to the end. If you want to watch for more podcasts in the future, follow us on YouTube, on Spotify, as we'll be uploading more and more episodes. We'll be inviting your favorite tutors on this podcast to share more. And if you have any topics you want us to discuss, just drop it in the comments. We will talk on those topics. If not, goodbye, everyone.